Hey, revision. My topic today is the ACA1234. Is it good for demos? Because, yeah, there has been a video on YouTube that popped up in, I guess it was December 2021, um, where the ACA1230 something, I'm not sure whether it was the 34 or the 33N, was compared against a different product, and of course also the Blizzard 1234, I guess. No, Blizzard 1230 Mark IV, which has always been named as a reference. And in that video, anything worked better than the ACA 1230 something. And yes, the video disappeared pretty quickly. The people who made it obviously found out that it's not a good idea, bashing others, maybe even in a non so factual way. And But I still got a chance to see it, and I started investigating. Most of these demos were pretty old. One that I specifically remember is Nexus 7. Nexus 7 is the winner demo from the Party 1994. It's by Andromeda, and it just runs a little jerky on the ACA 1230, 1233N, for example. And at some point, it just gets stuck. It doesn't continue to the next effect. It was always clear that this has to do something with caches, because all these demos ran fine on accelerators that allow instruction cache in chip RAM, like the Blizzard 1230 Mark IV. And and this is what the seminar is mostly about. It's about caches, it's about how the CPU is handling them, and what the accelerator product can do to increase the overall system performance or the system stability. This shall by no means be a seminar about modern caches. We're focusing on the 68030, which came out in 1990. Remember that it was impossible to have megabytes of caches on the chip back then. The cutting edge process back then was 1.0 micrometers. The CPU manufacturers were barely figuring out how caches actually work and how they can improve the speed. As a general rule of thumb, the caches on the 68030 increase the speed by about 20 to 25%, depending on the memory speed. And how does it do that? I kind of already gave the answer to that. Because it has to do something with memory speed. The performance of a processor can only be as fast as the memory where the instructions are read from. So if the CPU needs to wait for these instructions, the overall execution will be slow. If the CPU can read the instructions really fast, execution will be fast. So the faster the memory, the faster the CPU. So the simplest way of answering the question, what is cache? It's kind of a memory accelerator, but of course it's not as simple as that. It's a different type of memory, way faster, but also a lot more expensive, which is why there is not very much of it. The size of the cache in a 68030 is 256 bytes for instructions and 256 bytes for data. This is arranged in 16 bytes in 16 cache lines each, and the memory controller, or the cache controller, will create copies of the data that is read from external memory. So if the CPU will need the data a second time, then the copy will be available from memory that is a lot faster, so wait times are shortened. In order to tell if the contents of the cache are what the CPU is actually looking for, you of course need to store more data. That is the tag. The tag contains not the complete address, but 28 bytes of it. 24 bytes of these are stored just as the address, and another 4 bytes are the index, the so-called index, which decides which cache line to use. And there are another 4 bits that say if a cache entry is valid or not. 4 because 16 bytes is 4 long words. The 68030 works long word wise, and it will always execute enough bus cycles to gather at least one long word, which completes the cache line entry. This of course means that all the other cache line entries can only use or share the same tag entry. That means they are only available to memory locations that are adjacent to what has already been read. Keep this in mind, it'll become important later on. Now the lower 4 bits of the tag entry will make the decision of which cache line is actually used. This is really the simplest way you can approach cache, because you do not have to make a decision, any complex decision, on which line to use, because it's already inherent in the address. There are more modern ways to approach this. They are called multi-way associative cache. So a certain entry cannot or has a lower probability of overwriting another entry, but that's not what we're going into here, because this is about the 68030. And it really has a very, very simple approach to cache. So the address makes the decision which index to use, which cache line to use, and there is really no doubt about it, no complexity added. So next time the CPU will need that memory entry, it's already in cache, and it will be able to continue execution without having to wait. And voila, processing is faster. So far, I've only talked about reading. And but there is of course also writing to memory, and writing is really a very, very simple approach. Once again, this is a 1990s processor or 1990 processor, and whenever a write is happening, it is directly going to memory, and there is of course the and there are 2 possibilities that can be selected in the cache control register. That is the write allocation flag. So either a write to memory will allocate a place in a cache line, or it won't. This is something that is usually switched on in an Amiga, and I don't even know if there is any tool that that can make this change. To my knowledge, it's always on, because if you switch it off, performance goes down considerably. This approach is called write-through cache, and it means that any write will always go to the external memory. Again, this is a very simple cache approach, and executing a write immediately is reducing the complexity a lot. But now it's time to talk about cache coherence. Cache coherence means if a cache entry has the right tag for something that the CPU wants to read right now, it always assumes that the cache entry contains the same as the original memory. Now, in pretty much every 1980s computer, this is the case, but the Amiga is different. The Amiga has DMA, the Amiga has a blitter, and it has floppy DMA that can write to chip RAM. And this is where the memory contents, the chip RAM contents, and the cache contents can get out of sync. That means the chip RAM contents have changed, and the CPU didn't notice. Now, the Amiga does not have any provisions to even notify the CPU that something has changed. And vice versa, the 68030 CPU does not have any provisions for some external unit to say, please wipe that cache. The only possibility we have is to tell the bus controller in the first place, well, you're getting this data, but you are not allowed to cache it. This is of course a possibility in chip RAM, but it might also happen in fast mem if you have a SCSI controller that has DMA. This is the reason why I have decided, well, something can change in chip RAM. The CPU doesn't notice, and therefore it is not a good idea to switch on caches. My personal decision was to inhibit caches on all my accelerators up until the 1234 came out, and then it turned out this was only half right. For fast mem, the decision is easy. Most of the fast RAM that has been implemented on pretty much any accelerator for the Amiga, especially the 1200, there is no way that anything can do DMA into that. So you just always allow caches. That's a no-brainer. Same for ROM. ROM never changes, no matter how hard you try. So you can also allow caches on ROM. And for the 68020, it stops about here because the 68020 only has now for the 68020 it stops about here. This is how far they came in 1984, 1985 when the 68020 came out. For the 68030, they went a lot further. The first thing they did is they added. The first thing they did for the 68030 is they added the data cache. So they have twice as much cache, but for a different purpose. One is for instructions, the other is for data. And both are 256 bytes in size. So same arrangement, 16 lines of 16 bytes each, or 16 lines of 4 long words each. Another novelty of the 68030 versus 68020 is bursting. A burst means that the cache controller or the bus controller will always attempt to fill the cache line as fast as possible. Now, remember what I said about the tag? The tag of a single cache line is shared between the 4 long words. So these 4 long words can only be consecutive in memory. And consecutive is exactly what most external memories, DRAMs, and of course also modern SDRAMs, what they can do best. Once you have one word in memory, it is very fast to get the next entry in memory and fill up the cache line. The speed you gain is about 3 to 4 times faster. So this is really significant and of course, this doesn't speed up the processor by 3 to 4 times. Like I said, it's between 20 and 25% in practice. But the individual memory accesses, the consecutive memory accesses, they are the ones that are really fast compared to just a random access. Look at this diagram. This comes from the 68030 data book. It shows how the bus controller will try to fill a cache line. In this case, it happens to start at the very first entry and fills the cache line all the way to the end. So it's making 4 long word accesses to memory. It happens to start at the beginning. This of course means that the first access can happen anywhere in the cache line. And the Amiga OS has no provisions to make sure that the binary is loaded to a specific address. So at one time it is loaded that an instruction starts at the beginning of a cache line, and if you load it another time, then the instruction might be located in word number 2, number 3, or even at the end of the cache line, which is the reason why you get different performance data if you launch tools like AIBB or sysinfo 2 or 3 times in a row. You just close and open it and you get a different result, and the reason for that is cache alignment. Now, look at this diagram. This is also from the 68030 data book, and it shows a cache line fill that starts at word number 2 instead of number 1. And in order to fill the cache line, it wraps around at the end, and the last access is to the first entry of the cache line. Now what this means is it is going back in memory. Now if you think this is code, most of the code is executed forward and not in reverse. And therefore, this is wasting cycles. My accelerators, the ACA123x, has always stopped the burst at the end of a cache line in order to save these cycles. And this actually gains even more performance. Not a lot. It's in the order of 1 to 2%, but it gains speed. All the other accelerators from the 1990s, they just fill the cache line up to the end, wrap around, and make it complete, just like the cache controller is attempting. But like I said, I found that the CPU is actually faster if you do not wrap around. So I abort the burst at the end of the cache line, and if a fetch is happening to the last entry of a cache line, then I am not making a burst at all. So I'm only making a single access there. Now back to Nexus 7. Obviously this demo failed because cache was not available in chip RAM, and this demo has been written for an Amiga without any fastmem. So it had all its code and all its data located in chip RAM. At the time, it was very expensive to have fastmem in the Amiga, and of course the rules for the Party 1994 was obviously a stock Amiga 1200. As I pointed out earlier, it's not a good idea to cache a value from memory if there is a chance that some other entity is changing that value and the CPU won't notice. It looks like it took over 10 years for anyone to discover that that this is actually a problem. So we're really talking about a corner case here. Like I said before, the 68030 makes a difference between data and instruction cache, and the 68020 only has instruction cache. It turns out that when Commodore has designed the Amiga 1200, they have decided that caches in chip RAM are allowed, because then, although the computer doesn't have any fastmem, it will appear faster. And that is something that is questionable to me, at least. So you might ask, why does it work? Well, it's probably because the caches are small, they are not multi-way associative, and it is rather unusual to move code with a blitter and then jump into that code right away. In fact, the only time I can think of something like this happening is when a track loader is doing its MFM decoding and then jumping right into that decoded area with the cache having become incoherent that way. And this is something that is very unlikely, obviously, because nobody has ever complained. Then again, Commodore has introduced the CPU cache disable button in the early startup menu. And that must have been there for a reason. They probably anticipated problems with titles that were written for the Amiga 500, which has the 68000 without any caches at all. So these problems wouldn't arise there. Switching on data cache with the 68030 on the 1200 is something that fails pretty quickly. If you start the workbench and try to click on something, it just doesn't work. So the compromise that I decided on for the 1234 is to make instruction cache in chip RAM switchable. With the latest update of the ACA tool, we then have the possibility to switch on instruction cache in chip RAM. And if I save that to the card, I can run these demos. However, if you have an MMU and if you have the one of the new operating systems from Hyperion, like OS 3.1.4 or OS 3.2, these usually activate the MMU, and the MMU has the capability of disabling caches again, regardless of what the hardware externally says. So if my accelerator tells the CPU it's okay to cache this, then the MMU can override that decision, and that's exactly what the new OSs do. So it is possible that if your MMU is activated, then the demo will still not work, although all the provisions hardware-wise are given. So the only chance you have is either not to activate the MMU, or to just switch off the ACA123x completely. Both is possible without opening your computer. And personally, I like to watch the demos in their natural habitat. That means the exact target machine that they were written for. Now, if a demo came out for an accelerated Amiga, it is very likely, or no, it is very unlikely that it places code in chip RAM, or the other way around, it's very likely that it places code in fast RAM. And that means it will work regardless. It will always have the best speed available. On the other hand, a 1994 piece of art that takes advantage of every single cycle that the chipset provides, that's kind of a miracle that it works if you do a major change like update the CPU. It's really kind of a miracle that it just works flawlessly like here. Conclusion: are our accelerators suitable for demos or not? I believe they are, and I believe there is no other 68030 accelerator that is better suited for demos than the ACA123x, because you have the possibility to switch it on, switch it off. You have the best flexibility in terms of cache control, and you even have the possibility to slow down if you believe that something is too fast, or if you just want to try your own software on something that is a little bit slower. And of course, you can downgrade to a stock Amiga 1200, which means you can select the exact configuration that a certain demo was written for.
So, what do you need for demos? Well, first of all, performance. Every cycle counts. The demo scene, of all people, should know that. Compatibility. Older software couldn't possibly know about a new accelerator, so if a higher speed or new knowledge leads to fundamentally new design decisions, these should be switchable, so old software will continue to work. I have argued for a long time that putting code into chip RAM is bad practice, but in some cases, the rules of the party where the demo was released didn't allow anything else, so who am I to argue with the rules of the time? The best compromise is indeed to make features switchable, down to a complete stealth mode of the accelerator. Some knowledge of the inner workings can't hurt. This doesn't mean a deep understanding of the hardware, but the basic principles of how things influence each other. There's no point in just flicking all features on. This has never worked for any expanded retrocomputer. You might want to call it, with great features comes great responsibility. I am open to backporting the instruction cache in chip RAM feature to previous accelerators, but well, of course I'll have to find the time for it. If you already have an older iComp accelerator that doesn't have the feature yet, there is no need for you to buy the new one. And last not least, the demo scene is about respect. I have no problem with anyone pointing out an issue with my products, but I do have a problem with anyone attempting to use something as creative and as unifying as the demo scene to cast a slur on someone just because you didn't find any other way to promote your hardware. And that's a pity, because the mere fact that you've made an Amiga accelerator is a huge accomplishment. Kudos to you.
That's it from me. thanks for watching, and have a good time either at home or at one of the satellite parties.